This is what we're going to work with now, the Inviscid Burgers equation. Basically, the only difference is that now we have a velocity that is not constant. In fact, it depends on the solution. So at every spot in the solution, the velocity of propagation is different, which means that some parts of the solution can get ahead of other parts of the solution, and many times that leads to wave steepening, for example, and which can translate into a shock. So this is how shocks form in this equation. This is what we're going to be looking at. Now, this is perhaps one of the standard forms you might see the equation, or this on the other side equal to 0, but there's another very important way to write this equation, which is called the conservative form. And in conservative form, this equation looks like this. In either side of the equation, I can put it equal, or I can put it on the other side. But the important thing is that all of the space derivatives appear in the gradient. So basically, I don't know if you recall, in the beginning of the course, we talked about some of the fundamentals of the governing equations, and I told you that I had put a little 5-page write-up in Blackboard for you to remind yourself of conservative laws, the conservation laws. And a conservation form indicates that all of the space derivatives appear in the gradient operator. So we just put the u inside the gradient by a little bit of a small little trick there. And, or in other words, we can also write it as du dt equal to minus dE dx, where obviously E is equal to u squared over 2. So these are exactly equivalent, of course. And we're going to use alternatively these two forms. So this term E is because all of these terms appear here in the gradient, it's associated with the flux term, so it's called the flux term. And this is how we're going to use it. The physical interpretation of this equation I already said this, but let me just repeat, is that it corresponds to a wave propagating with different speeds.
You say different speeds, you mean like the top is propagating faster than the bottom?
Yeah, I mean, imagine this is the speed, right?
Yeah.
So speed is equal to the solution. So at every point of the solution, the value of that speed is the solution itself, and so it's a different value. So if you have a solution that looks like this, okay, and this is u, okay, obviously the value of u here is quicker than the value of u here, so the velocity here is going to be quicker than the velocity here, which leads to the steepening effect that I was talking about, right? The value of the, before we had a constant here on the speed. Before it was just c. Everywhere, every part of the solution moves at the same speed. Now we have a solution, a speed that changes at every point. So the wave propagates with different speeds at different points. Such that eventually a shock will be formed. You can see that from exactly this cartoon I've drawn over here, because after a certain time this might look like that, as the parts that move faster start getting ahead of the rest of the solution. This is our model equation, and it's amazing the amount of physics that you can get from this very simple equation. And we can generalize when we write it in this form right here. It's very easy to generalize it for other values of the flux term. So we could generalize the analysis that we do for where E is some other nonlinear function, and we have a variety of other equations that one can get, which are nonlinear equations where E has another form. It's just any function of U that you can imagine. You get lots of variety there. And also we can generalize it to more dimensions, and you can add the dimensions, and then you will have here E. It's going to be like a vector. And you can still generalize the analysis and some of the derivations we do by writing in this form. This is what we'll do. Okay, so let's start with the Lax-Friedrich scheme for our nonlinear convection. And recall, this is an explicit first-order method. And basically, it's the essence of the Lax-Friedrichs method is that we just introduce this trick of replacing the value U and I by the average. That's all it is. So we're going to write, so we can write it straight off the top of our heads. N plus 1 at I is equal, and here I put the average of U and I, and it's the average between the points on each side, I plus 1 and I minus 1. And the other part is the usual that we had for, in this case, it was a central difference, and if you recall, the central difference with a forward time was unstable, but this trick over here stabilized it. So we can use the center difference here. And this is now E at N, I plus 1, minus E N I minus 1. For our case, the particular case of the Inviscid Burgers equation, of course, E is equal to...
So shouldn't that first term be UN I plus 1 plus UN I minus 1 if it's the average?
This term?
Yeah.
Yes, it's a plus. Thank you very much. It's a plus. At N, though, the previous time. Both are at N and the points on each side. Yes, thank you. So this term, again, and we just write explicitly here delta T over 4 delta X, and we put explicitly what the flux term is for these two. Let me use a square parenthesis here since I'm going to use a curled bracket here. I plus 1 squared minus U N I minus 1 squared. So you can see there that this we can already write in code form. It doesn't have much tricks. And so let's look quickly at stability. Now recall that stability applies for linear systems. So in order to study stability, we need to linearize first. So to linearize our finite difference formula, we're going to use like an average speed, or it could be a maximum value, or some normalizing value for the speed. And so we write for a U, suppose U is just an average local value of the solution. And then we're going to write this as, from here, un plus 1 at I is equal to, again, this average un I plus 1 plus un I minus 1. And here we're going to use a value of u, which is our average, and delta t for delta x. And here we have our solution, but just 1 is not squared any longer. So now we consider a waveform, a normal mode like this, un I equal to Vn e to the I, the imaginary number, k I delta x, where, recall, phi is k delta x. So we can write now in the discretized equation, if we put this in the discretized equation, we can get Vn plus 1 e imaginary I and then index I phi equal to Vn and 1/2 e I plus 1 phi plus e I minus 1 phi minus Vn. Let's see if it all is going to fit here. U delta t divided by delta x, or for delta x. No, I'm going to use a. It's a 2. So un squared half was when I put u inside of the ddx, right? But so when I consider it as a linear equation with an average velocity, this guy is a constant now. This guy is a constant, and so I don't have the 1/2. So I made a mistake here. This is here just a 2. From this 2, from the final difference formula, and I have it over here as well. 2 delta x, and the same terms e I plus 1 phi minus e I minus 1 phi, and I managed to fit that there. So recall your, let me remind you here of the usual trigonometric relations that we always assume and take for granted just in case, so that you can see the process here. The sine is sine of c, ei z minus e minus iz, and divided by 2. And the cosine is the same but with a plus, right? Just a reminder. We've used this before without quoting the actual formulas. I just want to make sure that we now follow. This is serves as a review of our von Neumann stability analysis, with the amplification factor G equal to Vn plus 1 divided by Vn. Of course, here in this equation I can divide over by Ei phi, capital I, little I phi, and you see what we're going to get. So then I can divide over by Vn on the other side and use these equations up here. You can see over here that I have 1/2 e to the I capital, the imaginary number phi, and e to the minus I phi, and it's exactly the cosine. You can see right there. So cosine phi. And here I have this term again, u delta t divided by 2 delta x. And we have exactly the sign, but multiplied by the 2. And I think this is a 2i over here. It's an I over here. Yes. And so we have 2i sine phi. Okay, so continuing here, our modulus of g is equal to cosine squared phi plus u delta t divided by delta x, the 2 cancels out, squared sine squared phi, which we can rewrite using the standard trigonometric identity for the sum of the squares of the sine and cosine. 1 minus u delta t over delta x squared sine squared phi. And from here you can get the stability requirement. For stability, you see that we're going to need delta t over delta x less than, here we have this u value, and so 1 over absolute value of u. Now this is very interesting because it indicates that stability now changes with the solution, right? You need the Courant number in this case without the c, so delta t over delta x, to be less than 1 over u, 1 over the average value of the solution in absolute value. Okay, now we can go to the Lax-Wendroff. And now remember that we derived Lax-Wendroff based on a Taylor expansion. So again, we're going to consider a Taylor expansion. Our equation is different. And so we write u at n plus 1, I, is equal to u n I plus delta t times the first derivative of u with respect to t plus delta t squared over 2, and the second derivative, utt, of course these also add u at n and I, plus etc. So recall that we use the actual equation to get some expressions for our derivatives here. So the equation in this case is, and I'm going to write it in our abbreviated form where the derivatives are just subscripts, so it's ut minus ex, so this represents derivative of e with respect to x, and so we take now a partial with respect to t of this equation to get utt equals to minus the mixed derivative, which we assume that we could swap here. So we write in that way. So now note that dE dt, remember e is a function of u, And so we can write this as dE du times du dt. Where I've spelled out my partials there so you can see it more clearly. And that's dE du. Well, now for du dt, I use my equation, and that is minus dE dx, using my equation. And we write this as minus a dE dx where a has a name. It is known as the Jacobian. And again, this can be generalized to higher dimensions, which is the nice thing. That's why we treat it this way. In higher dimensions, it gets all easier as well to treat. So let's continue. We have we want the second order derivative of u with respect to time. So second order du dt, and that's going to be equal to, from this here, the partial derivative with respect to x of et, where et is right here, so partial derivative with respect to x with a minus d dx of minus a dE dx. Okay, of course, the minus cancels out, so d dx of a dE dx. In this case, we have E is equal to 1/2 u squared, and therefore A, which is equal to dE du, is simply equal to u. That is for the case of the Inviscid Burgers equation. So now we want to put this in the Taylor expansion. And we have un plus 1 at I is equal to uni plus, and here we replace our du dt. So we have delta t times du dt, and we replace that using the model equation. Let me write it all with the partials. Minus dE dx using the model equation plus delta t squared over 2. And here again we can use what we just obtained, which was d dx a dE dx, and plus our higher order terms, which in this case are order delta t cubed. So thus we have the following we can make the time derivative here divided by subtracted by uni and divided by delta t equal to minus dE dx plus delta t half. One of the delta t's was divided out, d dx a dE dx. Plus our higher order terms, in this case order delta t squared. And so now we can use we can approximate the spatial derivatives here and we're going to use central difference here. I'll write it in the next slide. Except run out of space, so I'll let you finish that. We'll just write the spatial derivatives in there. So we have un plus 1I minus uni divided by delta t equals 2. And we had the first minus the first derivative of e with respect to x, so we use our center difference here, I plus 1 minus ei minus 1 divided by 2 delta x. And the other term, plus delta t half. And I'm going to have, let's see, here I'm going to have a d dx. I'm just going to write it like that, d dx. All of this at n, at, and I, so I'm going to use the midpoint here, I plus 1/2, and I minus 1/2. And so this one is divided by delta x. That's the difference between those two mesh points. So we're using the midpoint for a second order approximation of a flux term. Now, for this term, we are going to incorporate the following approximation. We're going to write all of this term inside the parentheses here. A d dx n I plus 1/2 minus a d dx n I minus 1/2 divided by delta x, and we're going to use the following approximation. We're going to write a n I plus 1/2, and I'm going to, for d dx, write e at I plus 1 minus e at I minus 1. Oh, sorry, I'm going to use just a backward difference here, so this is just I. Of course, both at n divided by delta x. So notice that these two guys are on each side of I plus 1/2. So that approximates my dx at I plus 1/2, because each one of these points is on each side. There's like a center difference there. So A is the other one, AI minus 1/2. And here we have EI minus EI minus 1, both at n. And all of this divided by delta x again. Okay. Okay, now we're going to evaluate the Jacobian at the midpoints. this, we evaluate at the midpoints as basically the average on each side. And so we're going to get 1 over 2 delta x times a at I plus 1 plus a at I. Both of these are at n. The other one stays the same. I've put the delta x in front here, so I'll just write e n I plus 1 minus e n I minus 1 over 2 delta x, and I do the same for this a over here. I have a at I plus a at I minus 1, both at n, and this term carries over. And of course, all of this is divided by x. Remember that for the Inviscid Burgers equation, that we're going to work with, a equals u. So we already know how to write this in a computer program. We've got everything. So finally we have un plus 1. So finally we have it in a form that we can write in a computer program. uni, we multiply by delta t, and so we get minus, this term was already here, delta t divided by 2 delta x, e I plus 1 minus e I minus 1, both at n. And we have this pair of terms, additional terms here. They're delta. Remember, we had a delta t here, so I multiplied over by another delta t. I have delta t squared, and I have a 2 here, 1/2, and another 1/2, and delta x squared. So you see 1 delta x, 1 delta x, 1, 2, and 1, 2. So I have 4 delta x squared multiplied by this same thing, but I'm going to put u instead of a to write u I plus 1 plus u at I multiplied by e. Remember, e is also u squared, but I'm just going to keep the e for this. It's not going to fit. So I'm going to write minus here ui. That's a plus from here. ui minus 1 n e I n minus e I minus 1. Here we have the whole scheme. Again, stability requires, we're not going to do it, but you were just reminded how all this goes. Again, you will find that stability requires that delta t over delta x has to be less than 1 over the magnitude of u, where u is some maximum value of the solution locally. It changes the solution just like in the previous case. This is an effect of the nonlinearity. We're ready with, basically this is step number 2 of the new assignment.